So the next thing I want to introduce is the superposition theorem. Superposition means that you can analyze a complex system by breaking it down into multiple parts and treating them separately, and when you add them back together, you'll get the right answer. We see this often in physics, and it's superposition that allows the Norton theorem and the Thevenin's theorem to work. And we can use it directly to analyze circuits with multiple sources in a fairly intuitive manner. So I'm going to begin by looking at this circuit and solve it using the node method. So here's the ground node. These two nodes are equivalent. They're all actually one node. And so I really just have node A and node B that I want to calculate. And so I have to sum up the currents flowing into them. So I'm going to start with A. I have IA flowing in. And I'm going to say that the current flowing through R2 is I2 and that it's flowing this way. I don't write it down, but that's what I want. I guess I can actually draw it in here. That's I2 because it goes through resistor R2. And I1 flows this way and IV flows that way, from minus to plus through the voltage source. And so that's the node for the equation for the first node, summing up the currents. For node B, I have this equation exactly the same. Now IV flows in, IB also flows in, I2 flows out, and I3 flows out. Okay, so the next step then is to replace each of these currents with the equivalent voltage source. So I2 is just VB minus VA over R2, current flowing that way, so I plug that in. I1 is just VA minus 0, current flowing that way. IV is what it is, and I can't plug it in yet because I don't know it. And then likewise for this equation, I know IB flowing in, IV I still leave, and VB minus VA R2 again, and VB over 0 because current flows that way, plug in. Now the key to solve using the node method when you have a voltage source that's not connected to ground is just to write out explicitly the equation for the voltage B minus the voltage A, which you know has to be V. So VB minus VA equals V. Then plugging in this equation into here, I then have these equations, and I can rearrange them so that I have IV separately in each case, and therefore I can eliminate IV. So I've used both this equation and rearranged to get IV over here. And if I set these two equations equal to each other, I get this. Right, so, and then I can pull all the known things, the currents over here, and the voltages on this side. I want to pull out this voltage here, which is a known value, onto the other side. So on the left-hand side, eventually I have only things that are determined in the system. And then on the right-hand side, I'm left with just voltages, just the voltages here. And the only thing I'm left with is VA in this case. And so then I can solve for VA by dividing out that piece, and I get this equation. And notice I have a term for each of the three sources. They have their term, and they're each proportional to it with some combination from the rest of the circuit. To find VB, I only have to add V to it, to VA. And notice when I add V to that, I can recombine this term to get this term. So that V times R plus 1 R1 plus R3 over R1 plus R3. If I add this to it, then I'm just left with the R3 on top. And so I've solved the equation. I've solved for the system, the voltages at all the nodes, using the standard node method. Now I want to show how I can do that using the superposition method. So in superposition, we turn off the independent sources. We turn them all off. And we have to understand what that means to turn off a source. And we only consider one of them on at any given time. So let's begin with the voltage source on. I leave it in. And I turn off the two current sources. And what does it mean for a current source to be off? It means that no current flows, I equals 0, no matter what the voltage is. Well, that's exactly what happens if you have an open circuit. In other words, no connection between the leads flowing into the turned off current source. So remember, a turned off current source, always replace it with an open circuit, which means no wire or anything connecting the two leads. Okay, so now I have a simple system. I ignore these parts. I have a voltage, and I can neglect R2 entirely. Basically what I have is the voltage sends a current around this loop, and that's just R1 and R3 now form a voltage divider, but ground is in the middle. So when I do that, I have that the voltage at A, here's my voltage divider equation, and I have V, so the part of it comes below 0, and then VB has the part that's above 0. Then I turn off the voltage source. Now, turned off voltage source means there's no voltage independent of the current. And that's exactly what happens if you have a wire connecting it. So a turned off voltage source I connect with a short circuit, in other words, a wire. Notice I've gotten rid of R2 in this case because no matter what R2 is, as long as it's not 0, the wire dominates. And even if it is 0, then I have two parallel wires, which is the same as one wire. In this case, I have basically I1 flows through R1 and through R3 in parallel. And so the current then in IA flows through both R1 and R3, and R1 and R3 are in parallel. And so, and VA and VB are the same because they're a short circuit. So VA and VB, they're both the same. The current flows through the two resistors in parallel, so I write down the equivalent resistance for a parallel circuit, and I find the voltage using Ohm's law. If I turn on IB, I have exactly the same situation, just a different current. And now, to find the voltages for these two things, I just add up these parts in each case, and I get the same equations I had before. So summing up the parts, but this can be done in a much more intuitive fashion than in just doing the node method completely.